Alright, hello everyone. Today we'll be going over and continuing where we left off on the previous video, and we're going to be going over some more practice examples and then covering them over. So if you're ready, let's begin and dig into it. Okay, so for decimal to hexadecimal. So for this problem, we're converting from decimal, which right now is the base 10, into hexadecimal, which is base 16. That means instead of just grouping by tens, we're grouping by 16. So the method we use here is a repeated division because it tells us how many groups of 16 fit into the numbers. So when we divide 172 by 16, we get 10 with a remainder of 12. The remainder is important because it becomes part of our final answer. Now in hexadecimal, values above 9 uses letters, so 10 becomes A and 12 becomes C. We then divide the quotient, which is 10, by 16 again and get 0 with a remainder of 10. Or on hexadecimal version, it'd be our hex version would be A. Finally, we read the remaining remainders from the bottom to the top, which gives us AC. And the reason why we read from bottom to top is because each division step moves us from the least significant digit to the most significant one. Okay, so for this one, we're going to be going in the opposite direction. So from a hexadecimal to the decimal, since the hex is base 16, each position represents a power of 16. The idea here is that we convert each digit into a decimal value and then multiply it by its positional weight. In this case, B represents 11 in decimal. The 2 is in the 16 to the power of 1 place, so we multiply 2 by 16 to get 32. Then with B is in the 16 by the power of 0 place, we multiply that by 11. So we do 1 times 11, and then we add those together, giving us 43. This method usually works because of the positional number systems that we use to represent the values as a sum of powers from the base. Okay, now we're converting a binary to octal. So to convert from binary to octal, we take advantage of the fact that the octal is base 8, which is 2 times to the power of 3. So that means that every group of 3 binary digits corresponds to 1 octal digit. So instead of covering or converting the entire number directly, we can just group the binary number into sets of 3, starting from the right. If the leftmost group doesn't have enough digits, we can also add zeros to it. So after grouping, we convert each group into its decimal equivalent, which directly gives us the octal digit. This method is efficient because it avoids doing like full base conversion calculations, and instead it relies on the relationship between the powers of 2 and 8. Alright, so now we have octal to binary. So we reversed the idea from the previous problem. So since each octal digit represents exactly 3 binary digits, we can then convert each digit independently. So instead of doing division or multiplication, we can just simply replace each octal digit with like the 3-bit binary equivalent. So for example, 6 becomes 110, 7 becomes 111, and then 5 becomes 101. So then we just combine those groups together. And so this method works because we're just using the octal and binary as they're related to each other by the powers of 2. So this is just going to make the conversion straightforward. Alright, now we have hexadecimal to octal. So basically this conversion is just like a two-step process really, because there's no direct grouping between the base of 16 and the base of 8. So first we're converting the hexadecimal to the binary. Since both bases are powers of 2, each hex digit just becomes 4 binary bits. Once we have the binary number, then we can just group in sets of 3 to convert it into an octal. And this works because the binary acts almost like as a bridge between the numbers and the powers of 2. So by converting that through binary, we can avoid like complicated calculations, and we can just get it straight through there. Alright, so now we have an octal to a hexadecimal. So here we use the same idea as before, but in reverse. So since the octal and the hexadecimal don't align directly, we can just convert the octal to the binary first, and then the binary to the hexadecimal. So then each octal digit becomes 3 binary bits, and then we regroup those bits into sets of 4 to match the hexadecimal. If needed, we can also add some leading zeros to complete the groups. Then we convert each 4-bit group into a hex digit. And so the reason this method is used because it provides like the binary provides a consistent like intermediate way that makes it the conversions between different bases easier and then more systematic to using them. Okay, so now we're doing hexadecimal to binary. So this is honestly one of the most simpler versions of conversion, just because the hexadecimal is directly based on the powers of 2. So each hex digit is going to respond exactly to 4 binary bits, so instead of doing any arithmetic, we can just simply replace each hex digit with its binary equivalent. So for example, B becomes 10111, and then 3 becomes 0011, and then F becomes 1111. And then if we combine them together, this is what we get. And then this method is just fast and reliable because it just uses fixed mapping between the hex and then the binary. So now with this problem, this is basically just the reverse of the previous problem. So since each hex digit represents four binary bits, we can just group that binary number into sets of 4, starting from the right. And then we can just convert each group into a hexadecimal equivalent. So this is going to work because 16 is equal to 2 times the power 4. So each group of 4 binary digits directly links to 1 hex digit. And so this just basically is efficient and avoids needing to convert through the decimal. Okay, so for this method, instead of dividing, we're actually going to be building the binary number by subtracting by the powers of 2. So we start with the largest power of 2 that is less than or equal to the number. If it fits, we subtract it and mark it as a 1 in that position. If it doesn't, we mark it as a 0. We basically repeat this process moving down to the powers of 2. This method works because honestly binary is just an essential component towards the combination of it. So we're honestly constructing that combination step by step as we keep moving along. Okay, so on this one here, we're actually applying the same idea, but with the powers of 8 instead of the powers of 2, just because it's an octal. So we determine how many times each power of 8 fits into the number, starting from the largest. So then each result becomes a digit in the octal number. This method just, again, it helps us show the structure of the number system more clearly, since each digit represents how many groups of power that exist. Alright, so for this one, this is honestly similar to the previous problem, but now we're using the base 16, so we're determining how many 16s fit into the number. We're subtracting that value, and then we're going to continue with the remainder. So any value above 9 is represented with letters. So again, this method reinforces how hexadecimal numbers are built from the powers of 16, and then they help visualize where each of the digits are coming from once again. Alright, so for this one, we're just honestly converting again binary to decimal. We use the positional values, so each digit is going to represent a power of 2, and from then on we add the values where the digit is 1. This works because the binary numbers are essentially just the sums of the powers of 2, so by identifying which powers are currently present, we can then just reconstruct the decimal value directly from it. Okay, so for the last one, this is basically the same positional idea, but with the base 16. So each digit represents a power 16, and then we multiply each digit by the positional value, and then we add everything together. And so this method is just going to work for any base because all the number systems follow the same positional structure, and that's how we're able to get our answers from it. All right, and that's all for now. I hope you enjoyed. Thanks for watching, and please feel free to like, comment, share, and subscribe. Thank you, and have a good one.